Content in this presentation is covered on pages 95 through 97 of your textbook, and it's meant to help you achieve learning objective number 19, which is to summarize the 6 processes by which water changes from one state of matter to another. For each of these, indicate whether energy is absorbed or released. Be sure to skim the pages 95 through 97 before watching this video, and be sure to read carefully before attempting the online quizzes. As we said in the last presentation, water is the only substance that naturally exists on Earth as a solid, a liquid, and a gas. Because all forms of water are composed of hydrogen and oxygen atoms bonded together to form water molecules, the primary difference among water's 3 phases is how those molecules are arranged. Ice is composed of water molecules with low kinetic energy, so they don't move much. They're held together by mutual molecular attraction, hydrogen bonds. The molecules form a tight, orderly network and are not free to move relative to one another. Rather, they vibrate around fixed locations. When ice is heated, the molecules move more rapidly. They start to vibrate more intensely. And when the rate of molecular movement increases sufficiently, the hydrogen bonds between some of the water molecules are broken, causing melting. In the liquid state, water molecules are still tightly packed together, but move fast enough to be able to easily slide past one another. As a result, liquid water is fluid and takes the shape of any container that is holding it. When liquid water gains heat from the environment, some of the molecules acquire enough energy to break their hydrogen bonds and escape from the surface, becoming water vapor. Water vapor molecules are widely spaced compared to liquid water and exhibit very energetic and random motion. These processes are reversed when water vapor returns to a liquid state and when water freezes. When water changes state, hydrogen bonds either form or are broken. Whenever water changes state, energy is exchanged between water and the surroundings. For example, heat is required to evaporate water. The heat involved when water changes state is measured in units called calories. 1 calorie is the amount of energy required to raise the temperature of 1 gram of water by 1 degrees Celsius. Thus, when 10 calories of heat are absorbed by 1 gram of water, the molecules vibrate faster and a 10-degree temperature increase occurs. Under certain conditions, energy may be added to a substance without an accompanying rise in temperature. For example, when the ice in a glass of ice water melts, the temperature of the mixture remains constant at 0 degrees C until all the ice is melted. If the added energy does not raise the temperature of the ice water, where does the energy go? In this case, the extra energy breaks the hydrogen bonds that once bound the water molecules into its crystalline structure. Because the energy used to melt ice does not produce a temperature change, it's referred to as latent heat. The energy stored in liquid water is released to its surroundings when the water freezes. So melting 1 gram of ice requires 80 calories, an amount referred to as the latent heat of melting. The reverse process, freezing, releases those 80 calories per gram to the environment as the latent heat of fusion. So now we'll be thinking about the importance of latent heat of fusion. And you can imagine it's an important thing for things like frost prevention. Latent heat is also involved in evaporation, the process of converting liquid to gas. The energy absorbed by water molecules during evaporation is used to give them the motion they need to escape the surface of the liquid and become a gas. This energy is referred to as the latent heat of vaporization, and it varies from about 600 calories per gram for water at 0 degrees C to 540 calories per gram at 100 degrees C. So notice that, that in the figure we saw on the last slide, it takes much more energy to evaporate a gram of water than it does to melt the same amount of ice. During the evaporation process, the faster moving molecules escape the surface. As a result, the average molecular motion, or the temperature, of the remaining water is lowered. And hence, the expression we said a couple lectures back is that evaporation is a cooling process. So you experience this every time you get out of the shower or a swimming pool, right? Evaporation of the water that's on your body makes you feel cooler. In this situation, the energy used to evaporate water comes from your skin, right? That evaporation is driven by the energy from your skin. And so that's why you feel cool. Condensation is the reverse process, and that occurs when water vapor changes to the liquid state. During condensation, water vapor molecules release energy, known as the latent heat of condensation, in an amount equivalent to what was absorbed during evaporation. When condensation occurs in the atmosphere, it results in the formation of fog or clouds. Latent heat plays an important role in many atmospheric processes, and in particular, when water vapor condenses to form cloud droplets, latent heat is released. That warms the surrounding air and gives it buoyancy. When the moisture content of air is high, that process spurs the growth of towering storm clouds. In addition, the evaporation of water over the tropical oceans and the subsequent condensation at higher latitudes results in significant energy transfer from equatorial to polar locations. You're probably familiar with those last two processes that we illustrated. Sublimation and deposition are two others, though. Sublimation is the conversion of a solid directly to gas without passing through the liquid state. Examples you may have observed include the gradual shrinkage of unused ice cubes in a freezer, and also the rapid conversion of dry ice, which is frozen CO2, to wispy clouds that disappear quickly. Deposition is the reverse process, the conversion of a vapor directly to a solid. And an example is water vapor deposited as ice on solid objects like grass or window panes. Those deposits are called white frost, or simply frost. And the process of deposition returns the combined energy released by the condensation and freezing to the environment. Use the content provided here and on the Canvas site as well as outside internet sources if you'd like to investigate further, to verify that you can formulate answers to these questions. If you can comfortably answer these questions, you're in great shape for the midterm. If you can't, review the textbook, rewatch the video, and see if your abilities improve. If you're still completely stumped, start a discussion on the Canvas site or ask me for help.